Good. So we are still in chapter 10, which is on carboxylic acids and carboxylic acid derivatives such as esters, amides, acid chlorides, acid anhydrides, all those things, which in some sense have a similar reactivity and in some sense also a very different reactivity from aldehydes and ketones. I mean, there's some ways in which they can be compared, but I would say they are more different than similar in terms of their reactivity. We ended off last time with the idea that you can prepare carboxylic acids from nitriles. I felt I rushed through that. I wanted to make sure that I gave at least a reasonable example. So the idea is that if you have a nitrile, for example, this one here, you can hydrolyze the nitrile by heating it in dilute aqueous acid, and you will get the corresponding carboxylic acid. Again, what I mean by corresponding is it will have the same number of carbons as the nitrile. So you could say, in fact, you should say, that the nitrile carbon eventually becomes the carbon atom in the carboxylic acid carbonyl. The nitrogen in the nitrile winds up in a molecule of ammonia, or you could think of it as winding up in an NH4+ ion, since ammonia will pick up a proton from the aqueous acid and become protonated. So you can think about it either way. But the major organic product, which is the one we really care about, is going to be the corresponding carboxylic acid. Nitriles like this, in turn, can be made by doing a substitution reaction on an alkyl halide. So this could also have been, this is an alkyl chloride. It could also have been an alkyl bromide or an alkyl iodide. If we treat this with sodium cyanide, then you get the nitrile that's 1 carbon longer than whatever you started with. And you'll also get an inorganic side product, in this case, sodium chloride. But so this is kind of, this could be a 2-step sequence. You could start with the alkyl halide, make the nitrile, then take the nitrile and hydrolyze it. And it's a way of going from an alkyl halide to a nitrile and then to a carboxylic acid. So I just wanted to make sure that I gave at least one really clear example of that before we went on. But I want to continue today with the idea of nucleophilic acyl substitution reactions in both carboxylic acids and related compounds. I want to make sure that we clarify what we mean by nucleophilic acyl substitution. And I want to go into a little more depth into some examples, at the very least, Fischer esterification and hydrolysis of esters. And if we have time to talk about aminolysis of esters, we can do it. Otherwise, we can save it till Monday. I don't think any great harm will come if we save it until Monday. I think we'll have plenty of time on Monday. And yes, we will have class on Monday. I feel like these last few classes might be a little shorter. I for some reason don't feel confident in the amount of content that I have. I hope to give you at least, 35 minutes or so of content. I'll try my best, but we might not always go the entire 50 minutes. And then again, we might. I also tend to surprise myself with just how much I can talk. So I think part of the reason that there is less content than there might be is because I made the mistake on several levels of not requiring attendance. But when I do require attendance, I would have a daily clicker session. And even in the cases where I just gave all the clicker points for attendance and just did a little exercise, you got to figure that's still going to take anywhere from 5 to 10 minutes, at least 5 minutes. So it does add up. But I will have to take stock if we have just too many short classes at the end of the semester and think about adding another chapter next time. I feel very good about adding chapter 13. I think that did us some good. That material turned out to be relevant. I feel even better about deleting chapter 6, even though, again, I made some references to chapter 6 here in your class notes. So you should, of course, ignore those. I don't expect you to have mastered anything in chapter 6. We've never done it. It's not part of the course material. You're not responsible for it. But we'll see. We'll see how this goes. We'll see, especially how the the chapter on polymers goes. I just am not sure that's going to be something that requires 2 whole class days. It might be more like 1.5, but we'll see. And I can make that decision the next time I teach this. So that being said, of course, well, no, that's okay. We don't need to go there. So we have our example of formation and hydrolysis of nitriles. We've already talked about nucleophilic acyl substitution in general. And in terms of a general scheme, we said that it involves some carbonyl compound of this type. And one thing I didn't say when we introduced this general scheme before is we call this group Y the leaving group, because it involves doing exactly that. That group is going to leave. It's going to be some sort of group that the bond between carbon and Y is easily broken. That is not the case, by the way, for aldehydes and ketones. Let's just put a few. Here's a ketone over here. Let me also, a couple things I forgot to do, actually. I forgot to mute chat. Nothing personal chat, but I also forgot to open the chat box just in case chat has a question. So we'll put that over here. And here's a typical ketone. And these bonds in the aldehyde and the ketone, that carbon-hydrogen bond, and of course this carbon-carbon bond, are not easily broken. So that's why those guys don't undergo substitution reactions. They undergo addition reactions. But derivatives of this type tend to undergo substitution reactions, in which some nucleophile comes along and you get a product. Again, speaking very generally and roughly, you get a product of this type plus whatever that leaving group piece is. That could be either an anion or something neutral. That just varies. But I realized I didn't mention that the group Y is called a leaving group. So I wanted to clarify that much, at least for sure. Types of compounds that can undergo nucleophilic acyl substitution. Well, but types of compounds that can undergo nucleophilic acyl substitution include the ones that we've mentioned: carboxylic acids, esters, amides. Nitriles really kind of belong in that class. As we've seen, certainly acid chlorides and anhydrides. So we've covered all that already. But at the moment, we're going to mainly today be talking about carboxylic acids. They can undergo nucleophilic acyl substitution, and you know what those are. I'm just going to go carbox acid. We've talked about esters. That's not an ester. That's an ester. Those can undergo nucleophilic acyl substitution. And we'll also get to amides to some degree, as well as acid chlorides and anhydrides, those mostly on Monday, I would expect. But one idea your book also brings up here is the idea of a cyclic ester. So I just wanted you to be aware that those exist. You can have a compound like this. And cyclic esters are called lactones, L-A-C-T-O-N-E. So that type of compound is a lactone. You could also have one with a 6-membered ring. Those are the 2 most common lactones. And these can also be substituted. You could put methyl groups or whatever you like on those carbons. But either one of those would be what we call a lactone, a cyclic ester. Cyclic amides also exist. We'll maybe get to those later. But next, I want to move on to some examples of reactions of these types of compounds that fall under the category of nucleophilic acyl substitution. So maybe what I'll do, I'll see what it is I can fit up in here. The first such reaction I'd like to go over is called Fischer esterification. And as the name implies, it implies making an ester. What we're going to do is making an ester from a carboxylic acid and an alcohol. And the reaction does require an acid catalyst. Needs acid catalyst in order to go at any appreciable rate of speed. Basically the idea in general is we're going to take some carboxylic acid and we're going to add some alcohol. Actually, let me make that of a different color. I think that'll look nicer. We'll call the alcohol HOR2. And those we bring together in the presence of some acid catalyst, usually a few drops of sulfuric acid or something like that. And what we wind up getting is an ester. And you will also get out of this a molecule of water, which is just an inorganic side product. And so you can see what happens is effectively the alkoxy group in the alcohol and the OH group on the carboxylic acid switch places. So this is an example of a nucleophilic acyl substitution. This falls under the definition of substitution reactions as we originally gave it. We said a substitution reaction generally involves two groups switching places. And that's exactly what happens here. So the alkoxy group in the alcohol switches places with the OH group on the carboxylic acid, and you get your ester this way. I have an example of Fischer esterification in your class notes, starting with benzoic acid and ethanol, where I bring you through all the steps, which I hope to help to make some sense out of this here. I just want to say, I'm going to just draw it out again, even though it's in your class notes. I'm going to draw it out again here on the whiteboard, but the part that I'm about to draw is already in your class notes. So it might still do some good to copy it down, but just don't panic if you don't get absolutely everything, perfect, because you have it already in your class notes. I just want to, the main thing I want to add to the class notes that I wish I had originally is what's going on in each step. So to give an example of a Fischer esterification, let's talk about benzoic acid reacting with ethanol. I can use ET for ethyl group, right? In the presence of an acid catalyst to give ethyl benzoate, which looks like this. And of course, you'll also get a water molecule. And again, that example already is in your class notes. So let's start with our carboxylic acid. In the first step, we're adding ethanol and we're adding an acid catalyst. The first step of the reaction involves protonation of that carboxylic acid carbonyl oxygen. And that's not too surprising, because we've said that in carbonyl compounds in general, this oxygen has a partial negative charge on it and tends to be protonated, at least when we're in an acidic solution. So that first step is not too surprising. That's an acid-base step. That's just a simple acid-base reaction. The acid, which is actually going to be the conjugate acid of ethanol, is going to give up a proton and protonate that carbonyl oxygen. In the next step is an addition step. And what's going to happen is ethanol is going to add to the carbonyl. And we did say, you're saying addition. I thought this was going to be a substitution reaction. It is in a net sense. But the way we do the substitution is we do an elimination, an addition first, and then an elimination. So you'll see, hopefully you'll see all that when we lay out the entire thing. But the next intermediate, and I'm not going to go through the whole mechanism with curved arrows. I don't think that's really a good use of our time here. But here is your ethanol molecule that has added. So you can see over here, that's the addition portion. The ethanol molecule is now added to the molecule, and that's an addition reaction. Then we're going to have another acid-base step. We're going to remove the proton from this oxygen so that it goes back to being neutral, goes back to having a zero charge. So you get this intermediate. We then do another acid-base step. And so what's going to happen is now we're going to put a proton onto one of these OH groups. And it does not matter which, because they're the same. So you could put it on either one of them. And you'll get an intermediate that looks like this. At that point, you have your elimination step. And what's going to happen is we're going to lose this water molecule over here. That's going to act as our leaving group now. And by leaving group, I mean it does exactly that. It literally leaves from the molecule. And so you will get whoops. The octet rule is always a good thing. So let me do another color. This OH over here becomes this OH over here. So we're going to lose a water molecule. So that's how we do the substitution in nucleophilic acyl substitution. In general, you're going to find it's an addition followed later on by an elimination, give or take a bunch of these acid-base steps. And indeed, the only thing that's left is one more acid-base step. We'll simply remove the proton from that oxygen using actually an ethanol molecule. And we'll get our neutral product, our ethyl benzoate ester. So it's 1, 2, 3, 4, 5, 6 steps all told. And again, not concerning ourselves with arrow pushing or mechanisms or anything like that. I think that's more than good enough. So, those are the steps we take in Fischer esterification. Yes. Well, I would say, what are the key takeaways you should take from Fischer esterification in terms of what will I put in the exam? Haven't written the exam yet, but I would certainly have an understanding of the pathway of this reaction, that it involves an elimination and rather an addition and an elimination step. I would be aware that there are also these acid-base steps. I don't care if you memorize this particular example. That wouldn't be the way to go, because it might show up as a different ester. Yeah, but I would get the general idea from this. And I might have more to add based on this question. Third step, 1, 2, 3. Second step, this one. Okay. Oh, I see what you're asking. We're with the hydrogen on the oxygen over here. Yeah, I see what you're saying. I should have clarified that. This OH group becomes that OH group. So it's still there. Well, that's whether it's positive or negative has to do with the number of bonds that are attached. This oxygen has Right. 3 bonds in 1 lone pair. So it's, yeah. I could have drawn out the oxygen-hydrogen bond. That might have made it a little clearer. And like I said, all of these structures are in your class notes. So you don't have to worry about missing it. All I really added was what each type of step was, since I think that kind of clarifies it a little bit. Good. Other questions about Fischer esterification? You're going like this goes here, goes here, goes here, which, yeah. This goes to this, goes to this. And again, I could have taken any other carboxylic acid and I could have taken some other alcohol besides ethanol. I will say generally in real life, when we do a Fischer esterification, the alcohol we use is almost always either ethanol or methanol, because those are the easiest to get a hold of. They're the easiest to get rid of. The excess at the end of the reaction. So nearly always it will be one of those two. Good. Let me just see. One other important point. You'll notice that Fischer esterification is something we say can only be done under acidic conditions. You'll notice in all of these schemes here, we always have acid added. Let me go over why that is, that it needs to be done under acidic conditions, since I think there's a very good reason, and I think it's one you will understand. Fischer esterification must be done under acidic conditions. Let's consider what would happen if we tried to do something like this under alkaline conditions. Let's say that we took some carboxylic acid. We'll just take this one over here, R1CO2H. There's our carboxylic acid. And let's see what would happen if we took our alcohol HOR2 and maybe some base, maybe some hydroxide on it. What would happen is this base would immediately deprotonate the carboxylic acid, like we just talked about in the last lecture. We said that you can treat a carboxylic acid with a base, like sodium hydroxide or sodium bicarbonate, and you will wind up with a salt of a carboxylic acid. And here I don't mind showing the mechanism because it's just one step. The base reaches out and grabs the proton off of the carboxylic acid. We break the oxygen-hydrogen bond, and we get the salt plus water. OH minus plus H plus gives you water. And so that's the reason why it must be done under acidic conditions, not alkaline. If we try doing the reaction with base, with say hydroxide ion, then all that will happen is the base will deprotonate the carboxylic acid, and this carboxylate salt is now dead. It will not undergo any further nucleophilic addition or substitution. Because in order for this to undergo nucleophilic acyl substitution, we need some nucleophile to add to that carbonyl carbon. We need something with extra electron density, some Lewis base. That's what we mean by a nucleophile. We need that to add to the carbonyl, and that's now not going to happen. This compound or this species already has a full -1 charge. It doesn't want to receive any more electron density. So that's the reason why Fischer esterification must be done under acidic conditions. Otherwise, the carboxylic acid will just get deprotonated and no further reaction will happen. No further reaction occurs. So that's the reason why it must be done under acidic conditions. If you tried doing the reaction with base instead of acid, all that would happen is you'd deprotonate your carboxylic acid, you'd get your carboxylate salt, and that would not react any further. That's why we need to do a Fischer esterification under acidic conditions only. So you do need to add a catalytic amount of acid. And as I said, that will generally be a little bit of either sulfuric acid or phosphoric acid. I think those are the most common ones. Good. Other questions then? Oh, yes. Pointing at the carbon, this one here. This is, well, we need a nucleophile to happen here. Well, we have it, it's the alcohol, but it's not going to want to add because this already has a minus charge. It doesn't want any more electron density. So this can't happen. Here, the reason the ethanol can add, that by the way is the mechanism of that step, though I didn't really want to go over the mechanism here. But what happens is the ethanol attacks over here and breaks the carbon-oxygen pi bond. And it can do that because now this still is a plus charge. So this still wants electron density. This guy doesn't because it is a minus charge. So that shuts the whole thing off. Yeah, sure. No, good question. All right. Well, let me erase this side of the board. Interestingly enough, it turns out that the exact opposite reaction of Fischer esterification is also a nucleophilic acyl substitution reaction. And right. So this is going to be, I'm going to call this hydrolysis of esters. And this can be done under either acidic or alkaline conditions. Or let's say acidic or basic conditions. Both will work. And I want to bring you through those pathways also. What I hope to convince you of is that the acid hydrolysis of esters pathway is just Fischer esterification turned around backwards. It's exactly the same except it's backwards. And we'll also talk about why it happens. Under basic conditions, there's fewer steps involved. And again, all of the structures I already have here in your class notes. I'm basically copying off the class notes. I just want to give you a little more information about what's going on in each of these steps. So what I did in your class notes is I started with, let's see, example. I started with ethyl benzoate. And we're going to hydrolyze this in the presence of dilute aqueous acid. Remember, H3O plus implies that water is also present. You can't have H3O plus ions without water present. And generally, this also needs to be heated, but I don't know if we need to get quite that granular about it or quite that detailed about it. And so what you'll get is benzoic acid plus ethanol back at the very end. So this also is going to be a nucleophilic acyl substitution reaction. Effectively, one of the OH groups on water, which we have some water over here, is going to switch places with the alkoxy group in the ester. And it's essentially the reverse reaction of Fischer esterification. But the reason that this reaction is going to work as a Fischer esterification in reverse is because we've got a lot of water present. And so we need that water in order to drive the reaction forward. Whereas in Fischer esterification, there is no water present. It's done with the alcohol as solvent. And that's something that I want to be sure that I stress further before we end class today. But let's go through the pathway first. Let's start with our ethyl benzoate. So the first step is going to be an acid-base step. And we'll start by putting a proton onto that carbonyl oxygen. Nothing surprising. We've seen that type of thing already. This then is going to undergo an addition reaction. And we're going to add a molecule of water. I could even say addition of H2O. And so we get an intermediate that looks like this, which you'll see already, we're kind of near the end of the Fischer esterification reaction, but it's kind of the same thing except going in reverse. Then we'll have another acid-base step. We'll remove the proton on this oxygen. Actually, let me just, for clarity, add those lone pairs over there as well. So that's one acid-base step. We've removed a proton from that oxygen. And again, all of these structures are in your class notes. I'm mostly presenting it this way to slow myself down a little bit, because I worried that if I literally just taught from your class notes, I'd be like, the thing goes here and there, done. And I didn't want to do that to you guys. I figured this would slow me down a little bit. So after this, we're going to do another acid-base step. There's quite a lot of acid-base steps, it would seem. Actually, let me also put lone pairs on that oxygen. That oxygen now is a plus charge. So we get this intermediate. After this, we're going to have elimination of the alcohol. Elimination of, I'm going to say R2OH, which is our alcohol. In this case, R2 is ethyl. So we're going to have, as a result, OH over here. And let me just clarify that also. This OH over here becomes this OH over here. And after that, there's just one more step. That's going to be another acid-base step. We simply have our carboxylic acid. But this is where we lose the alcohol molecule. So we lose this molecule of ethanol and we get our protonated carboxylic acid. So I think it's still 6 steps, acid 2, 3, 4, 5, 6. Yep, it's still 6 steps, but they're pretty much in reverse order from the Fischer esterification. So, but I wanted to get the concept of each step down for you so that when you saw it in your class notes, you knew what was going on. And again, the main reason that this will now go in reverse is because we have water present. Again, remember, H3O plus implies that water is present. If you go back and look at the conditions for Fischer esterification, there was no water present. Yes, you generated 1 molecule of water partway through the reaction, but for that 1 molecule of water, there's probably 10,000 or 100,000 molecules of the alcohol, because the alcohol is the solvent in this reaction. In this reaction, the water is the solvent. So that's why it goes in the reverse order. The water drives the reaction forward by Le Chatelier's principle. Whereas in the other one, the absence of water and having a lot of the alcohol present drives that reaction towards formation of the ester by Le Chatelier's principle, which says if you add in more of the starting material, you'll drive the equilibrium forward. So that's something you covered in Gen Chem. Good. And I think that's all I really need to say about that. I just want to make sure I'm not missing anything. You know what? Let me think of a way to summarize what I just said. Reaction favors formation of carboxylic acid because the excess water drives the reaction in that direction. That's about the most concise I can be on that. Whereas with Fischer esterification, we didn't have excess water, quite the opposite. We had essentially no water. What we did have is excess alcohol. And so that will drive the reaction towards formation of the ester. So the reason for the different outcomes, even though the two reactions are pretty much opposites of each other, the reason for the different outcomes is because of what's present in excess and then because of Le Chatelier's principle. So I wanted to be sure that I summarized that for you, at least in some sense. Good. You know what? I just want to do one more thing. I think I'll leave ammonolysis of esters for Monday. As you know, I would rather go a little more slowly than a little more quickly, and I think we'll have plenty of time on Monday. Good. Any questions on that? So this is hydrolysis of esters under acidic conditions. I just want to talk about hydrolysis of esters under basic conditions. Yes. Well, I'm not. This is still acidic conditions. Right, and under those cases, we'll have water and OH minus. This is acidic conditions. We're going to do basic conditions next. Yup. And I think you guys will like that one better because there's fewer steps. Yeah, but this is under acidic conditions because H3O plus, aqueous acid. I also should say your book is using the term saponification. And I think that term is not wrong, at least when you're talking about hydrolysis under basic conditions. We used that term in the chapter on lipids when we were talking about making soaps. That was a saponification. It's actually what saponification means, is making soap. But I think the word hydrolysis is better because it's more general. It can be used for either acidic or basic conditions. So let's look at an example under basic conditions. Hopefully it will fit over here. I just changed the ester around. This is methyl hexanoate, 1, 2, 3, 4, 5, 6. And we'll take aqueous sodium hydroxide. And then we actually need an aqueous acid step, just dilute aqueous acid. That's only for the last step, as you'll see. And we're going to get hexanoic acid plus methanol out at the end. Just like over here, we got benzoic acid plus ethanol. We lost our ethanol molecule over here. So this is going to require somewhat fewer steps. We're going to start out with our methyl hexanoate. And we'll add our aqueous sodium hydroxide. This is going to be our addition reaction. So no acid-base steps. We just lead with the addition. You know what? I don't like it. I want more board space. I'm cramming everything in. Let's do this. I'll write all that down again. We still have 9 minutes. There's time. Maybe I'll even move that over a little bit. Example under basic conditions. We'll take methylhexanoate. First step will be aqueous sodium hydroxide. And then at the very end, we will need to add acid. OH plus CH3OH. So in the first step, we have aqueous sodium hydroxide, and the first step is going to be our addition step. There, this is better. Now I have enough room. So all that's happened is the hydroxide ion from the sodium hydroxide has added into our carbonyl group. So meanwhile, this O- used to be that oxygen over here. And that's pretty common to see species with a minus charge in basic solution. That's something we've seen before. That is typical to of species with a plus charge as intermediates in acidic solution, and typical to have species with a minus charge an intermediates in basic solution. After this, we immediately do our elimination. And that's going to then split into two parts. One piece is going to be CH3O-, and the other piece is going to be hexanoic acid. So, and now we're going to have to think a little bit carefully, because remember, we've got hydroxide ion around. Carboxylic acids react with hydroxide. So we're going to have to worry about that in a moment. This methoxide ion will simply undergo an acid-base step and pick up a proton from water and make methanol. So that's one of our products. But at the same time, there's still OH present. So we're going to have another OH- present. This is going to be our acid-base step. OH- still present. And what we'll get is the carboxylate ion. And then we just have one more step. That's when we need to add our acid, because we want to put the proton back on here. So when we add acid, that's the second step. When we add the H3O+, it's going to first take out all of the hydroxide. It's going to neutralize all the base. That equation you saw 50 times in Gen Chem. H3O+ plus OH- yields 2H2O. That's all there is to that. And then once the leftover OH- is gone, then it's going to put the proton back on the carboxylate. So this is going to be another acid-base step. And then we're done. So that's what saponification or hydrolysis under basic conditions looks like. And again, I just used methyl hexanoate as an example, just like I used ethyl benzoate over here as an example. I could have picked any other ester. So under basic conditions, there's far fewer acid-base steps. We just do our addition, and then we immediately do our elimination. And that gives us the alkoxide ion, which picks up a proton from water and goes to the alcohol. And we also generate a molecule of the carboxylic acid, but that's not going to stay as is. That's going to get deprotonated by the hydroxide that's still present. So the hydroxide is basically going to continue to react until there's nothing left for it to react with. And at that point, we'll have our alcohol, that's one of our products, and the carboxylate ion. And so if we want to isolate that carboxylic acid, we need to acidify. The acid will first neutralize any leftover hydroxide ion, and then we'll start putting the proton back onto the carboxylic acid. And so one more acid-base step, and we generate our carboxylic acid. And that's basically how hydrolysis looks under alkaline conditions. Somewhat different from acidic conditions, still the same basic idea, still an addition followed by an elimination. But there's fewer steps, it seems, under alkaline conditions. At least that's how it looks to me. And with that, I think that's actually a good place for us to stop. I don't mind leaving Ammonolysis of Esters until Monday. So, unless anyone has any questions, have a great weekend. I will see you all on Monday.